Hello physics students. So in this video, we're just going to focus on just one kind of wave, sound. So I'm going to start by creating a sound other than with my voice. What I'm going to use is this device over here off camera. It's this really cool device with all these dials that allows me to create a whole bunch of different kinds of sounds by turning these dials. I'm going to feed the signal out of this machine into this basic little cheap speaker. So let's start with, there it is. So you can hear the tone, and I'm going to talk later about what it is about this tone that's changing when I turn this dial like that. Before we get there, I first want to come closer so you could see how the speaker is constructed, and it'll tell us essentially what kind of wave this is being created. So what we have here is a magnet in the back of the speaker, and then inside we feed a current through here, and one of the things about current is it generates its own magnetic field which will interact with this magnetic field, and there'll be forces that attract or repel the coil in this paper cone right here so that this paper will go forward and backwards, and you could see that it's kind of cone shaped and it lunges like this based on the electrical signal that's received at these two pins. So right away we could tell that this wave, if this is going like this and it's sending sound out like this, it is a vibration that's parallel to the wave motion. It is a longitudinal wave. So let's summarize on the board. We got sound. What we need is some kind of source, a vibrating object. I had a speaker, but right now I'm using my vocal cords that are vibrating. Or remember earlier in this HM video, I had the metal tuning forks vibrating, and that created sound. So any vibrating object can create sound. So this is paper lunging forward and backwards, and when it goes forward, what it does is it pops forward very fast, and it squeezes the air molecules and packs them close together. That compresses the air, causes what we call a compression. But that speaker doesn't only just lunge forward once, it lunges forward, and then with this compressed air, like all compressed air, it will not stay in that region. Just like if you have a balloon with compressed air and you poke it with a pin, right, it explodes out. So this is going to explode out, and what will happen is that explosion will advance and compress the next layer of air over here. So that popping out compressed the next layer. And then what will happen is now this is like a balloon that's popped, and it'll rush out like that and expand outward and crush the next layer of air. And that pops, and so it just keeps, that compression keeps traveling through the air with a velocity like this that's parallel to the original vibrations, which makes it a longitudinal wave. Compressions, rarefactions, we could put another here, that's another rarefaction. This is obviously another compression, so label those as well. But an important thing in the Regents curriculum is to know that sound is vibrations passing through atoms. Without any atoms, in other words, in a vacuum, you cannot have sound. This speaker paper would be, say I'm in outer space and I hold this up and it's vibrating, I wouldn't hear anything. It'd be silent because there's no air molecules to crush, and then those compressed airs going into my ear are what my ear is hearing and registering, so no atoms, in a vacuum, in other words, no sound. So take a moment and copy these notes down. All right, well, sound travels at a particular speed. So that's the next topic, the speed of sound. So one number, 331, is the speed of sound, 331 meters a second. That's fast. That is like over 3 football fields in 1 second. So sound very fast. STP means standard temperature and pressure. Basically, that means you're at sea level and it's 0 degrees Celsius, so it's cold. And then sound will have the speed of 331. I stated that that's on the reference table. So front cover for all the numbers right here. So here we are, and then we see, speed of light, where is it? Speed of sound in STP, right here, near the top of the table. Let me back up so you could see. And they put it in scientific notation here, 3.31 times 10 to the 2, which is 331. So you could just write 331 meters per second, but it's on the front cover of the reference table. But I want to point out, oops, that's okay, that in general, the speed of sound is different at different temperatures and also different pressures, but more information than we need to know. You could calculate this approximate speed of sound on temperature dependence, like a room temperature is about 20 degrees Celsius, somewhere around there. So if you multiply 20 times 0.6, you get about 12. So 12 on top of 331 is about 343, somewhere around 340 meters a second. That's the speed of sound in a typical room. It's faster. You don't need to know that. You don't need to know this formula. I'm just putting it there for reference so you could kind of understand that the speed of sound, it's faster in warmer air, slower in colder air. And also an interesting thing, people think sound travels poorly in water. And the reason why a lot of people think of that is when they go swimming. And if they go underwater and they try and talk to their friend, you hear all this bubbling and you can't even hear what they're saying. That's because you're creating sound through air coming over your vocal cords, and then that air is going into the water. It's going to make bubbles and it's going to distort the sound. But if you had a speaker that worked underwater, a speaker designed for underwater, it travels very well sound in water, better than in air, clearer in air, and faster in air. And it goes further. So, you know, people talk about sonar being able to go across oceans, okay? So it travels well underwater, counterintuitive. And also in steel, people think, steel doesn't go in because steel's so rigid. Well, if you were to put your ear down on a railroad track and someone miles away took a sledgehammer, boom, and hit that compression on the steel would travel so rapidly, get to your ear very effectively. So it travels even better in steel, even better in stone than air. So very interesting because in substances that are very hard to compress, the speed of sound is actually very fast. Again, you don't need to know any of this. You just need to know that if they say something is happening at STP and it's a speed of sound problem, you've got to go to the reference table to find this number 331. All right, so what kinds of calculations would you have to do with sound? Let me make some room. Oh, I don't think I created a pause. Let me create a pause, allow you to copy this down. Go ahead and copy this down just for reference. All right, let me now state the relationships that, show you the math relationships that come up in speed of sound calculations. So here they are. Once you know the speed of sound, you could figure out how long it takes it to go a certain distance, or you could figure out for a given distance, how much time does it take for sound to reach you. So give you an example, let's suppose you're standing a football field away from a field goal kicker. So you're way out in the stands and they're at the other end trying to maybe kick an extra point. So let's say the distance is 100 meters, 100 yards, 100 meters, about the same. They kick 100 meters and it's a cold day, it's STP. So you put 100 meters here, 331 here, and you solve for the time, you would see the kick going in, off the kicker's foot. And then if you solve for time, 100 divided by 331, it's about 0.3 seconds. Just throw out a number there. So it would take you about 0.3 seconds. You see the kick, but you don't hear it. And then 0.3 seconds later, you hear the boom of the kick. Okay, so obviously the bigger the distance, the more time for a given speed. Another way this formula is commonly used is for lightning strikes. You've heard that I'm sure you have, that if you count the seconds of when you see the lightning flash to when you hear it, because the sound is slower than the light, you can determine how far away the lightning bolt hit. So let's suppose, you have 331, somewhere around there, and you see a flash of lightning, and you start counting, or you use a stopwatch, and you figure out that 5 seconds later, you hear the roar of the thunder. If you plug in 5 here, then you get about 1,600 meters away. That's where the lightning bolt hit. And just to give you an idea, that's about 1 mile. So every 5 seconds delay when you see the flash to when you hear it, corresponds to about a mile away. That's how far. So obviously 10 seconds later, then it landed 2 miles away. So you can gauge how far away the lightning storm is from the delays. This formula, of course, is on the reference table. So I'm going to talk more about it with some examples. But first, I want to point out that these two formulas are on the reference table. So this is all the way back in the mechanics section. You see the whole formula is d equals VIT plus 1/2 AT squared. Now, obviously, the sound doesn't accelerate, so we just use d equals VIT. The V equals lambda times frequency. I talked about that in the last video right here when we just talked about waves in general. It's in the wave section, V equals frequency times lambda. Okay, so let's make room for the next bit of notes. Okay, so I didn't create a pause yet, so go ahead and copy these notes down. All right, so the next thing we're going to do is we're going to just talk a little bit about, a little on a tangent, but it's a related tangent, human hearing. So as you know, you could listen to music, you could hear all kinds of sounds, you could hear low rumble of like a bass guitar, or you could hear something like a cymbal crash, different frequencies, it turns out. That's the difference between the tones of the sound. The lower the sound, like a rumble, like a bass guitar, the lower the frequency. And so the higher the sound, like when you hear a cymbal crash, then that's a higher frequency. So it's kind of matches lower frequency, lower tone. So what I'm going to do is unplug this little cheap speaker, and what I'm going to do is plug into another cheap speaker, these old computer speakers. They're just a little bit more efficient at making sounds. And I'm going to plug them into this device that allows me to just make any tones I want. And what I'm going to do is take you through the range of human hearing. You may have heard that there's some sounds that humans can't hear, like bats can hear higher, dogs can hear higher. There's something called a dog whistle. You go and you blow on it, and you don't hear anything, but your dog, because they could hear higher frequencies than you can. So what I'm going to do is give you a sense of the range of human hearing by taking you through that range with this speaker and this nice little device. So the lowest sound that humans can hear on average, because some people could hear a little bit lower, some people, have different, ears, but on average, the lowest sound that people can hear is 20 hertz, 20 hertz. And what I'm going to do is try and create it on this, but this is a cheap speaker, and so it doesn't make low sounds very well. Some of you may know car stereos have those big giant subwoofers that roar and get the whole car to shake, and that deep rumble you could feel inside. It costs a lot of money, right? You're not going to get that for whatever, $30 or whatever this is. But we're going to get a sense of what that is. So let me configure this correctly and turn it on. And you see it's kind of like a boop, 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 boop. That's not a good job creating 20 hertz. So I have to go higher for this speaker even to function properly. So that's about 50 hertz, 50. So more than double the range of human hearing. So, but the 20 hertz sound, what we're going to do is calculate the wavelength of a 20 hertz sound. So let's start at the low end. So 20 hertz. And to figure out the wavelength, we have to use V equals lambda times frequency, or frequency times lambda like on the reference table. Let's assume STP, so we go to the reference table, it's a cold day, and we find out that the speed of sound at STP 331, as I mentioned on the reference table, so we're going to plug in 331 here. What is the wavelength for 20 hertz? So obviously I divide both sides by 20, and what I get is, let's see, maybe 16.7 meters. Very long waves. So imagine you're hearing not these little speakers, but maybe someone's going down at the beach. They got the convertible top down. They're showing off with their speaker, and you hear the boom, 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 shaking all the street lights or whatever. So that sound, when that subwoofer lunges forward, just like this little cheap one, it lunges forward, it compresses the air, and that races out into space. The next time the speaker lunges forward, the first original compression is now 16.7 meters away. And so you can gauge that like maybe you've been in my classroom, so it's about the width of the classroom. That's how long the waves are. And as they come past your ear, and each compression then goes into your ear and hits it, then it vibrates your ear at 20 hertz, of course much faster, but 20 times a second, and your brain interprets that as that low rumble of low sound. So now, the high end, how high can we hear? Looks like I'm going to get a little crunched here. I got a little too enthusiastic, a little too big here. The highest that we can hear, on average, is 20,000 hertz. But some people could hear higher, some worse. I'll talk about that in a minute. So let me take you through the range of human hearing, and you'll probably turn down your computer because it's going to get a little annoying. So here's 50 hertz. I'll take it to 100. There's 100. I got to change the scale so I could take it from 100 to 1,000 now. So ready? Here's 100. 500. That was 1,000 hertz. We can hear to 20,000. We got a long way to go. We only went 5% through the human range and already sounds so high. Let me change the scale again and start at 1,000. And this time, this will take us to 10,000, halfway through our hearing. So 1,000, 2,000, 3,000, 4,000, 5,000. We're a quarter of the way through our hearing. 6,000, 7,000, 8,000, 9,000, 10,000. We're halfway through our hearing range. Let me reconfigure. So we got another halfway to go, just as high. So let's go. 10,000. That is, let's see. Oh, wait, I think, no, that's right. Yeah, 10,000, 12,000, 15,000, 17,000, 20,000. Can you hear anything? Maybe not. And there's a couple reasons why you might not hear anything at that 20,000 range. One is, this is a cheap speaker, so just like on the low end, on the high end, it also starts failing. You need a better speaker to make all the full range of human hearing than $20 or whatever this is. The second reason, which is also pretty likely, is you might already have hearing loss. Well, I shouldn't say that with a smile. It's a very sad and tragic thing. Nowadays, people have the headphones on. I hear them 20 feet away, and it's in their ears in headphones, blasting their ears, and they listen to music like that all the time, and it's damaging the ear because what happens, like when you work out your muscle, right? It gets bigger and stronger and tougher. When you start blasting your ear and giving it a good workout with some loud sound, it's going to get thicker, which means less responsive. And so you start getting hearing loss. Concerts, weddings. I went to a wedding this year, no, a couple years ago. It was so loud, I went outside, and there was like half the wedding was outside this dance hall. And outside, we couldn't even hear each other. That's how loud the music was through the walls. Inside, man, people must have lost a lot of hearing. So music just keeps getting louder, and concerts. Now, before I talk about why that's a problem, let me just calculate the wavelength quickly. So again, as I said, that sound goes the same speed as the low. Like I mentioned previously in an earlier video, this is the same. No matter you're doing bass or treble or high or low sounds, what changes is one thing gets big, the other gets small. This gets small, that gets big. So right now we have a big frequency, we're going to have a small wavelength. And, oops, when we divide, another mistake, by 20,000, we get a wavelength of 0.0167 meters. In other words, about 1.6 centimeters, about that long. So when we're making 20,000 hertz sound through a speaker, the speaker lunges forward, and then that compression goes out the same speed as the bass, but immediately right after we make another compression, and they're only this far apart. And those go by in our ear and strike it 20,000 times in a second, and we hear a high-pitched sound. So let me create a pause to give you a chance to copy these notes down. All right, let me make some room. Now, but I don't want to go on with the notes just yet. I want to just talk a little bit more about hearing loss. You may be, so where people lose their hearing first is in the high range. And you might be thinking, well, I don't need the high range. I actually used to think this too before an audiologist explained to me. I said, okay, well, here's 10,000. What do I need anything beyond 10,000? When people talk, they don't talk this high, right? Voices are more like maybe in this range, right? So in the hundreds of hertz. So I don't need thousands. I was wrong. Everyone talks and makes sounds. Right now, I'm making sounds in that 20,000 range. You might be saying, I don't hear any high-pitched whine. The high-pitched squeaks are when I say sounds like th for TH, s for S. Those are actually very high-frequency sounds. And when you start losing those, you start to have trouble understanding. So let me give you an example. You go to your grandma's house. She says, okay, tell me about your school day today. And you say, okay, so you say something like this. All right, I just thought of something with a lot of sounds that have these kind of high-pitched sounds. So the sassy student, Sasha, sat several inches to the side of me. It's an extreme example. But so your grandma, because she's 70, 80 years old, naturally you just lose hearing with age. So it doesn't have to be for abuse of ears. It can just be a natural process. Your grandma can't hear those kinds of sounds anymore. So what does she hear when you're telling her about your school day? She can't hear this. Maybe even this. No, probably. So you tell her about the school day, and your grandma hears e, to dent, everal, in, to, I'd of me. That's what your poor grandma hears. And she says, what? Can you speak up? I can't hear you. Poor grandma, right? But that's what happens when you start losing that high end. You cannot hear all those sounds that are so important to meaning, and you start trying to, everything you hear is a big logic puzzle. Your brain's trying to fit in all these pieces, and if there are too many, you just can't do it in time. The conversation moves on and you get lost. So that's hearing at the high end, why it's so critical to your life and understanding. All right, so you didn't have to write that down, but I just wanted you to understand, because like I said, as a teacher, I didn't know that, and then someone explained to me, so I was very grateful to have that explained. Last thing about sound that the Regents really likes, it's a very popular concept, the difference between frequency and amplitude. So you already sense the difference between frequency. So I'm going to, well, maybe I'll turn this down. You're probably saying, you had a volume control on that? Why didn't you turn it down earlier? I don't know. So here's the sound. Maybe I'll turn it down a little bit more. And what I'm going to do is increase the frequency. Now I'm going to decrease the frequency. So the sound didn't get any louder. It just became more squeaky. That's higher frequency. And then it became more like a bass rumble closer to that. And that was a lower frequency. So the first thing is, as the frequency of sound increases, the sound gets closer to a squeak. So that's the increase in frequency. So, I don't need to write any more because we just heard what that sounds like. What does amplitude of a sound then do? So what that means is, instead of having the speaker at this rhythm with a small displacement, I'm going to have the speaker at the same rhythm, but it's going to go with a bigger displacement. Same rhythm, or this same rhythm but more displacement. What that changes is the volume. Okay, so let me show you. So there is a particular sound frequency. Let me increase the volume. The amplitude. Let me decrease the amplitude. It's the same sound. It's just louder or quieter. That's amplitude. So let's jot that down. Where did I put my chalk? Oh boy, here's one. Okay. Let me create a pause to give you a chance to copy those notes down. All right, so that's sound. Very interesting. So highlights, I just want to remind you, sound is a longitudinal wave. That means the speaker lunges forward and backwards and sends the sound forward. So parallel vibration to the wave motion, that's a longitudinal wave. So that means it has compressions where the air is compressed and rarefactions where the air is stretched. But sound needs atoms. No atoms, like in outer space where there's a vacuum, no sound. But sound can go through air, it can go through solids, liquids. If there's atoms there, sound can travel. Then we learned that we can calculate from the speed of sound 331 right on the reference table. We could use D equals VIT to calculate either the distance sound travels in a certain time or the time it takes to go a certain distance. And from V equals lambda times frequency, we can calculate from, once we know the speed, which we could look up, or sometimes it's given. They'll say in a problem, the speed of sound in a room is 340, and then you don't use 331, that's only at STP. So if you know the speed of sound, you can solve for frequency or wavelength if you're given one or the other. And the last point, as here, frequency is the tone, amplitude is how loud it is. So those are the concepts and the calculations for sound in the Regents curriculum. I hope you enjoyed the physics. I hope the detours and I hope the tones weren't too annoying, and I hope the detours and the lectures about turning your music down so you don't damage your ear weren't too annoying. So I hope you enjoyed everything, and I'll see you in the next physics video.